test, it's also decision number 2. So if the test is fair or awful, don't bother. So that's the final answer of the problem. And we'll now look at the EVPI, and the expected monetary value of this problem is given up here in the final node, right? 796.76. So EMV is equal to 796.76 thousand. If you remember, we were looking at that bottom node after we had built it, right? If you go back to the bottom node, the one where we don't get the information, right? It was 74. So by collecting the information from the test, we increased the expected monetary value from 74 to 796. So it's, and basically what happens is if you run the test, and the test does provide some valuable information. Right now we're not talking about a disease, we're talking about a product, so it's not a life or death type of test. But, and again, the likelihoods indicate that the data that you get from the test aren't perfect, but it helps a lot to have that as test results, because if the test result says fair or awful, you don't bother with it, right? And so you don't roll out products. I mean, you might miss on a product, right? But you don't roll out products in many cases that might not perform, and you do roll out products that will perform. So you get a lot of benefit out of running the test. Okay? So last class we talked about EVPI, expected value of perfect information, and we said you compute this by doing the EV with PI and subtracting the EMV. So remember, the EVPI is how much you would pay for perfect information, right? This is the expected value of perfect information, right? So what's the upper bound that you would pay for better information, right? Well, right now we already have this test information, so that's pretty good, right? But how much more information could be beneficial, and how much more beneficial could more information be? You think of it this way: a perfect test, right? A test that would tell you exactly if the product is going to succeed or fail. So the key is we already have this information, so we need to be able to calculate this. So to calculate the EV with PI, one way you can think about this, and we kind of did this implicitly yesterday, is you can think about the following tree. You can say, if G occurs, and remember on the backboard we said G was a great market, right? Then what would you do? Well, if it's going to be a great market and you know it for sure, are you going to run the test? You don't need to, right? So you're going to have to roll out the product nationally, right? So your decision is going to be to roll out the product, right? You're not going to kill it, right? That's not going to be your decision. And if that happens, you're going to have a 10.8 minus 7 million, right? And so 3.8, we calculated this before, right? So that's going to be your payoff, right? And if the product is awful, if the product is fair, right? You remember that the benefit was 5.4 million if the product was fair, and the cost is 7 million. So if the product is fair, rolling it out is going to be a 5.4 minus $7 million deal, minus 1.6. So that doesn't sound too good. So in this case, you're not going to roll it out, you're just going to kill it. And that cost is going to be 0 if you know the product is fair, right? And of course, if you know the product is awful, the same thing is going to happen. You're going to lose a lot of money. This is a square, not a circle. You're going to lose a lot of money if you roll it out, right? You're going to lose a lot of money. So it's going to be, what was that, 1620 minus 7,000. So some big negative number, minus 58.
5380.
5480.
5380.
5380, thank you, 5380. Right, negative 5380. So you're definitely not going to do that. In this case, you're also just going to kill it. So you've got 3800, 0, and 0. The weighted average of those. And remember, the prior probabilities were what? 45, 35, and 20? I think they were.
Yep.
Prior probabilities were 45, 35, and 20. They're right.
Yep.
They're right here, 45, 35, and 20. So if you take the weighted average of 3,800 times 45, right? That's the value of having perfect information if you have a great market. 0 times 35, that's the value of perfect information if you have if you know you have an awful product, a fair product, and that's the value of perfect information if you know you have an awful product, right? And if you take the expected value of those three situations, you get the EV with perfect information. In this case, we have to multiply this, which is going to be hard to do in our heads. So let's do it with Excel. Equals 0,45 times 3,800, 1710. Okay, so going back up here, we've got 1710 minus, shall we just call this 797? So let's call it 797. So I think we get a 3, and then we get a 1, and then we get a 9. So 913,000. So what this says then is even though running the test, of course, is much better than not running the test, right? There's much benefit from running the test, right? It's worth up to another 913,000 to get even better information about the performance of the product, right? The test certainly helps a lot, but it's worth another 913,000 to get even better information about the product. Or another way of saying is we would pay up to 913,000 additional to find out more about how this product is going to perform. Okay? So you can build this. You kind of notice this is like a backwards decision tree, right? We have the conditional node on the first stage, and then we say, well, we know it's a good product. If we looked at a crystal ball and someone said, hey, that's going to be a great product. If the genie said that, then we would roll it out. If the genie said it's going to be fair, we know we'd lose money, so we wouldn't bother. The same with all. So that's one calculation. Now, we can also calculate another quantity. And we didn't have this before because we didn't have a sample. We didn't have a source of providing us with information up front, okay? So this is the last thing I'm going to talk about that's new. The expected value of sample information, or the so-called EVSI, okay? And this is essentially what this is going to measure is what is the value of doing this test, okay? What is the value of doing this test? So the EVSI, expected value of sample information, as opposed to the EVPI, is the expected value with free sample information. Okay, minus the expected value with no sample information. So it's actually not going to be too difficult for us to calculate this because we already actually have all these numbers. So essentially, make the test free. What would it look like if the tests were free? And then what would it look like if we didn't do the test? Okay? So you might actually be able to guess these numbers either from your tree or from what I've got up here. What's the value if I don't do my test? If I don't do the test market, what's my expected monetary value? Say expected monetary value. There's no sample information. It's right up there on the board.
74.
That's right. It's a tiny number, but it's up there, right? Right? So we subtract 74, right? If we don't do the test, 74,000 is all we can get. Now, if we run the test, but the test didn't cost 100, we can calculate the expected value with free sample information. So it's actually pretty nice, right? What we can do is we can go up here and we can either change this number right here to 0, or we can just go all the way back to whatever cell we were referring to here and change that number to 0. And if we do that, we see the expected value of the problem with free sample information is 897, let's just say. 897. So if you subtract these two, you get roughly $823,000. So essentially what we're saying is, this test would still be valuable to us for any cost between 0 and 823, right? Right now we're paying 100 for it, right? The 100 took us from here to here that we paid, right? For any value of the test from 0 to 823, the test is still worth it. We'll still make decision 1 here in the first decision. Let's do a little sensitivity analysis to check that. So I'll go back to 100. Obviously at 100, the test is worth it, right? If we go to 500, suppose the test costs 500, the test is still worth it, right? Suppose we go to 800, the test is still worth it. Suppose we go to 820, the test is still worth it. Suppose we go to 822, the test is still worth it. Suppose we go to 823. Now the test is actually too expensive. Okay? And that's because we rounded, right? It's 822 in a large fraction, right? Okay? So what we're saying is, and you can see that here, right? We're getting a lot of value from the test. This is the number if the test costed 100, right? So if the test were free, this would be 896, right? So we're going from 74 to 896. So we'll pay any amount between the difference between those two numbers for the test. It'll still be, obviously the cheaper the better, but, right? So this is the value of that test, the maximum value of that test market that we ran. And this is the maximum value of any test market that we could ever pay, or the maximum we would pay, that is, for any test market. So both EVPI and EVSI are interesting quantities. I'll make a comment here. You might say, well, and it's certainly true here, where we're assuming that sort of everybody makes decisions based on sort of completely rational basis, right? There's actually a section in the book and also a way that you can incorporate utility functions into this whole decision-making framework, right? So instead of using straight expected values, you can use expected utility, all right? We're not gonna do that, but you could, instead of taking weighted averages, like this number is computed as a weighted average of 3 numbers, you could compute weighted utility, right? And so that allows you a little bit more maybe realistic decision making, because you can incorporate the fact that most people are risk averse into that. And actually, I think if you look in tree plan, let's see here. Okay, it wants me to select a single cell. Let's see here. Let's see what happens here. Okay, I think it like that. Yeah, so, let's look under options. Yeah, so there's this exponential utility function that you can use instead of using straight expected values. The other thing I'll just mention about tree plan that might be useful, we're doing everything in our trees to maximize profit, but you can switch the tree to minimize cost if you want to look at the tree as a cost tree, as a minimum cost tree. So this is under the options, right? That's sort of normal. You can just make all your costs negative numbers and do the profit tree, and it'll still work either way. So that's fine. All right, I think we pretty much covered the stuff in chapter 14 that I wanted to cover. I feel like leaving this textbook here. I carried it around the whole time for a month. I think I'd be skinnier. Yes, we covered almost, not all, so we stopped at the utility part. We covered up to the base theorem part. We're not doing the multi-criteria decision-making model or other parts. So like I said, the final exam will be over chapter 14. I'll give you some practice exams so you can play around with it if you like, some homework problems. I'm going to give out the exam we were just talking about. I'm going to give out the exam on Friday. It's going to be due on Monday.
What? Like Friday, end of week?
Yeah, it's going to be due on Monday after weekend. And I'm also going to have the paper be due, the final version of the paper due on Monday night. So everything's going to be due on Monday night. I guess that would be January 29th.
Yeah.
Okay, we'll figure out a time. It makes sense.
I mean,
Can we use open books and notes?
It's open book, open notes, yes, but it's going to be your own work. So that's a requirement. So these classes are pretty intense, I know. They're intense for me, right? I appreciate the opportunity to come back here and teach this stuff to you. I learned a lot myself, actually, especially in the R part about how I have to change it to make it more, palatable to learn quick, And so